Hey everybody, in this topic we are going to be looking at summing up P5, which is domestic electricity. There's a little bit of review in the first two boxes here for P4, so for what happens for a series and a parallel circuit. Okay, so this is just a review from P4 about electric circuits in general. The first thing here is describe the current potential difference in total resistance of a series circuit with two bulbs. So first things first, current. Okay, which symbol is I. Okay, so current is the same in both bulbs. Okay, the potential difference, I'm going to call that PD, is split between the bulbs. Okay, but if I added it together, whatever potential difference I'm putting in, my two light bulbs are taking out that potential difference, and it's split between them. Okay, and the total resistance, okay, is add up the resistance of the bulbs. Okay, so what that means is that if I have one light bulb and I add another light bulb in series, my resistance has gone up. I have a higher resistance than I would have if I just had one bulb. Okay, now for a parallel circuit, okay, remember parallel is there is more than one path for the current to take. Okay, and in parallel, current is split. Current is split between the bulbs. Okay, the potential difference is the same on both. Okay, so this is the exact opposite of series. So in a series, you had current was the same, current is split. Potential difference is split in series, potential difference is the same in parallel. Okay, and resistance is lower with bulbs in parallel. Okay, so you actually get more current flowing overall the more stuff you hook up into parallel. Okay, what is DC? DC is direct current. Okay, this here, the current flows in one direction, and an example is a battery or a cell. Okay, AC is alternating current. Okay, you have current switches direction constantly. The potential difference goes positive, then negative, and back. And an example is mains electricity. So in other words, anything you plug into the wall runs on alternating current. Frequency and potential difference. Just give me 1 second because I'm going to go 100% by what the textbook says on this, because depending on the age of the source that you look at, you'll get different values. I know the frequency is 50 hertz. I'm just going to double check what they want me to say is the potential difference for in the UK. All right, having checked our all-knowing exam board textbook, it is 230 volts. Okay. What type of cable do most domestic electrical appliances use? I'm actually not sure what they're looking for on that. Most, I guess you could say they use an earthed cable. Just means it has an earth wire in it. Yeah, that's the only thing I can think of for what they're looking for with that answer, or that question. Okay, let's work our way down and back across this way. So, sketch 3 locations of the 3 wires in the plug. Describe the color, potential difference, and function of each wire. Okay, so this is the back of the plug. Okay, we are going to have one cable. So our cable comes in here. It has 3 wires. We're going to have a little fuse here and a terminal here. We have a terminal up here. And we have a terminal down over here. And we have 1 wire that goes in there. We have 1 wire that goes up into here. And we have 1 wire that goes in like that. So, first wire, right here, the one connected to the fuse, that is the live wire. It is brown. And it goes from plus to minus 325 volts. Okay, the live wire is the wire that makes you dead. Okay, you touch the live wire while it's plugged in, and it's the one that will make you dead. Okay, over here, we've got the neutral wire. It's blue, and it has 0 volts. You can touch it and you'll be fine. If you touch it and the live wire, you will not be fine. Okay, and the last one is the earth wire. It is green and yellow, alternating. And it is a safety. It prevents electrocution. Okay, basically if there was a fault with the live wire and it was touching the metal casing of an object, the earth wire provides a path so that the electricity will flow and burn out the fuse, as opposed to it waiting to discharge when you touch it. Okay. Yeah, that's it for that one. I'm going to jump over to these guys here. So when is work done in a circuit? Work is done when energy is transferred. It happens as the current flows. Okay, so if current is flowing, then you have work being done by the electricity. The useful energy transfer in a kettle, I'm going to go and say electrical, and we are transferring it to heat. Thermal energy. Okay, useful energy from an electric motor. Okay, again, electrical. And because it's a motor, it's kinetic energy. Okay, wasted, it doesn't say it, but I'm going to tell you. Wasted in this case is sound. And wasted. And there's actually some waste heat as well, because the heat that escapes is wasted heat. Here, our waste is sound, vibrational, and heat. Thermal energy, I guess I really should say it. Vibrational energy. Vibrations are wasted kinetic energy. Everything ends up as heat anyway. What two factors affect the amount of energy an appliance transfers? That would be its potential difference. Ooh, actually, cross that out. The power rating and the time it's on. Those are the things that will affect the power rating, or sorry, that will affect how much energy is transferred. I'm going to do the national grid ones last, so I'm going to do our formulas. So power, so I need to add units. So we know that power in watts is equal to, sorry about the lighting, it's just the way that it's falling here. Potential difference in volts, current in amps. The formula is P equals I times V. Here we've got watts again, you'd have amps, and you've got ohms for the resistance, that's an omega sign. Energy transferred in joules is power in watts times time in seconds. Energy transfer is charge flow in coulombs times potential difference in volts. You can also have energy transferred in kilowatt hours is kilowatts times hours. Okay, national grid. So what is the national grid? The national grid is the power stations, transformers, and cables that transfer energy. Electricity. So I'm just going to call it electricity. Okay, those are the three elements: the power stations, the transformers, and the cables. Your home is technically not part of the national grid. Your home uses the national grid. You are connected to the national grid unless you have some kind of crazy solar power. You are not actually contributing to the national grid, so you're not really part of it. All right, the purpose of a step-up transformer. This increases voltage or potential difference, increases voltage for transmission, in other words, to send it far. It increases efficiency. Okay. And the purpose of a step-down transformer is to lower voltage to the safe levels in your home. All right, there we go. That is most of the stuff. The only thing that's really not on here is doing some practice for these, using these formulas. So for that, I'd recommend some past exam problems. And if you are one of my students, you can also use Kerboodle, which has plenty of calculations worksheets, and I have made the mark schemes for those available. All right, good luck.